Welcome back to Further Solutions Academy. Further Solutions Academy. Don't forget to share to friend, subscribe if you have not subscribed before. And at this point, we have a lot of videos for you to watch. We have over 400 videos. You can come and learn any topic of your choice. Don't forget, if you want to reach us, you can comment below, or you make use of this line to reach us. Now, this line you can call us. You can WhatsApp us, and also Telegram is allowed. Either of the three, you are good to go. On this video, I'll be working on the types of metric space. This is our video 13 on the topology. Just try to come along with us. You will surely enjoy the course called topology. Now, I have type of metric space. That is what I have for you. By the end of this video, at least I should be able to touch some part of types of typology. Depends on my time. The first thing I want to understand now is that I'll be calling it the first one, which is A1. I call it excluding matrix. Now, when we talk about this, is a normal distance that we normally show. When you have my D, there must be a D, and that D must be a metric space which satisfies those conditions I mentioned earlier, that the distance must not be greater than equals to 0. It can only be equal to 0 if and only of the same point. I think we have done those things, and it must be symmetric, and also triangular inequality must hold. Take note of those three things. It means when I have a distance of this, which equals to this minus what? This is a distance. We call it, this also can be called standard metric space. The standard metric space, because it's also a standard, because we all know what is called standard. It's a normal way of measuring distance between 2 points. That is very, very way. It means, I think, when we talk about the distance of 2 points, you must understand what is called the complex side and the real part. Now, both of them will come to reality, which it will form a plane, which is I've told you, real axis and imaginary axis and the real axis. Take note of those things. Now, this next thing, another thing I want to mention now is what is called discrete metric space. Now, when we talk about discrete metric space, it's also called distance between 2 points. It's always equals to 1. When the distance between 2 points is always equals to 1, when you have an amount of a point together and the distance from them to them is always 1, that is called discrete topology. It means when I'm talking about a relation, like I have D related to x to x, and is on R. That is my R. Now it means my x comma y is just like we are having something like 0 to 1. That is, it means it will be 0 when this is equals to 6. It will be 1 when this is not equals to this. That is what I mean by what? Discrete topology. It will be equals to what? That is what I mean by what? Discrete topology. Now, my discrete topology, it means I will be talking about D of x of y will be less than equals to D of x and y plus what? D of what? Y and z. That is what I mean by what? Discrete topology. It means if this one, it will be less than equals to what? 0 plus 1. If this one is 0 and 1, it means this case they are equal. That is what I mean by discrete topology. Please take note of these things very well. Take note of this very well. The third one that will be mentioned now, I'll mention now, it will be called, the third one, it will be called Taxon metric space. Now, there is another third one. It's a task. Now, when you have about a point distance between 2 points, like for instance, you have a distance like this, and you have another distance like this. Now, like a street, let me use the word a street between two a street A, this is a street A, and this is a street B. Before you get to this, you must go like this, you come like this. Do you get me now? That is what I mean by tactical metric space. Now let me quickly use this to explain that. And I have something like this, I have something like this. Now call this place point Y, y1 comma y2, and I call this place the point, which is the coordinate, which is x1 comma x2 is a point. Now for me to go like this, I can come like this and get to this point here. Now I get to this point, but if another way, and I will go like this, 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 go like this. Now can you see? And that is what I mean by what tactical. Now going this way, that is what is called tactical metric space. It means we are talking about a street, like we are having several streets, and you want to get to another point, you must go, depend on the direction of that road. That is how it is being done. That's what is called tactical. It means my distance of this, of y comma this, it will be distance of I'm talking about x21 and y1 y2, it will be equals to this absolute value of x1 and plus absolute value of. Now that is what it means by tactical. Now can you see what that is? That is what. Now it must satisfy the condition of this of the condition of the metric space. The first one, d of x comma y must be it can be equals to 0 if and only if the x is equals to 0. And the next one is 2, d of x comma y, it can be this can be equals to this comma this. I think I've explained this in my previous video. And also triangular inequality also, this is called symmetry. This is called the symmetry property. Symmetry property. Please take note of that. And I can also call this x comma z can also be less than equals to d of xy plus d of yz. That is what I mean by that. Now, the next one I want to please, this three things property must hold here. That is what you can recall. It can be called what? That's topology. The next thing I need to understand, you need to understand, is called maximum. We call it maximum. Now, maximum topology. It means I have something max. It will be equals to the matrix of this, it will be maximum topology. It means metric space. It means, what I mean there is that max metric space, it means the highest and the highest point, which is the largest distance. Let me use the word largest distance. Largest distance. That is what I mean by that. For instance, if I have my Cartesian plane this way, I have my Cartesian plane, and I have, this is my point. This should be my point. This now coming to here, I can go like this and get to this point. Now, the one that has the largest, the longest distance, that is called what? This is the longer distance, because this place to this place is get to this. This is my x, this is my y. Now, that is the one that has the largest distance, that is known as what? Which is this in terms of direction, largest distance, or biggest distance, or between the direction, anyhow you call it. It means I will say that my d of r of n multiplied by cross of this which is going to be like that. It means I'm trying to say that x comma y is maximum of what? Maximum absolute xi minus y1 si. Now that is what I mean by what? That is what I mean by this. Now that is what I mean by maximum value. Now don't forget that first one we hold, second one we hold, and the triangular inequality we also hold. It means I can say that my d of y of this plus d of y of z will be equals to, it will be greater than, equals to maximum of and plus, which is for whole I, is in what? Is in half. Is in half. Now, it means these are high anyway. Yeah, I is in half. It means I can say that with what is on ground, I can say that of I plus I minus z, which is going to be this, we cancel this, back to normal, x minus z, which is that. I can now conclude by having this is greater than equal. It means I'm saying that d of xy plus d of yz is greater than equals to, this will be d of xz. D of xz. That is what I'm trying to explain there. That is what I'm trying to. Now, with this four that I've listed so far, let me try to show some proof, in terms of so that you'll be able to see how it works. Let's see some proof. Look at this proof. I have proof this metric space less than equals to d of xy plus. Now look at this question. Prove that this is less than this. It means d of xy less than equals to d of xy plus d of zy. Now that is what I'm going to prove. How do I prove something like this? This is z. This is going to be z. Now, how do I prove this? I've told you, in order to prove this axiom, we consider the possible cases. Now, hope you know the possible cases. The first one is that if I have case 1, look at my case 1. My case 1 will be equals to, if x equals to y equals to z, it means everything becomes 0. Everything becomes equals to 0. For instance, then if I have d of xy equals to 0, d of xz equals to 0, and d of yz equals to 0. What I'm trying to do here is that d of x comma y less than equals to d of s comma y plus d of y z. Now it means I'll be talking about 0 equals to 0 plus 0, which is 0 equals to 0. That is when I've told you that the only thing that will make something like this to hold is and only if they are of the same point. It means for x to be equals to y to be equals to z, it means x, y, z are of the same point. X and y are of the same point. Now, case 2 now. Case 2. My case 2 will just lie on when my this is equals to what? If x is not equals to y is equals to z. Now, at this point, the story will change. It means I can be saying that then I will be saying that d of x equals to 1 and d of xz equals to 1, and d of other one yz equals to 0. Now it means I'll be having, back to what I wrote the other time, I'll be having something like this. Oh, this is z, this is z, this is z, this is z, this is z. Okay, it means I'll be having of z less than equals to d of xy plus d of yz. Now it means I have this, as that, y xz is equals to 1, xz will be equals to 1 less than equals to, which is going to be equals to 1 plus 0. 1 is equals to 1. Can you see inequality holds also? Now the third case, which is, permit me to rub this also, the case 3 of this will be, now the case 3 will also comes to reality by saying that case 3, you can say that if x equals to y and not equals to z. Now that is what I mean by case 3. It means what will happen also, they will be equal. You know, I think that d of xy equals to d of xy plus d of yz, which I'll be talking about what? 1 equals to 0 plus 1, which is 1 is equals to 1. Inequality. Now, the last case, which is going to be 4, case 4 is that if 3 of them are not equal, that is the case 4, which is going to be the last case. Now, it means since they are not equal, this will now go d over, it means, and then let me just make it so clear, then d of xy it will be equals to 1, d of sz it will be equals to 1, d of yz it will be equals to 1. Now, with what I've done now, I can now say that what d of x, y, z will be less than d of s, plus d of y, z, which I will be having 1 is less than 1 plus 1, which is, you can see that is going to be now the condition is that now combining all 4 conditions together. Now, if you combine the whole 4 conditions together, which is d of x z less than equals to d of xy plus d of yz, which is going to be like this. It means for all x, y, z, for all x, y, z belongs to what? Big X. That is hence X is metric space. X is metric space. Okay, that is all about that. Can you see there are some cases and the way you generate the cases? In the next video, I will try to explain, more examples of metric space. Don't forget, we are home with Further Solutions Academy. Thanks for watching.